High above the Earth, a massive new instrument expands into orbit. This is NISAR, a joint mission by NASA and the Indian Space Research Organization. It is the first spaceborne radar system built to operate a dual-frequency synthetic aperture radar. This schematic details the physical scale required to make that possible. The structure relies on a 9-meter composite boom extending out to a 12-meter deployable mesh reflector, the largest of its kind ever launched. This shows the dual-frequency observation geometry. The payload fires two overlapping cones of energy on a shared physical aperture. The gold outer cone represents NASA's L-band radar to penetrate forest canopies, while the inner blue cone is ISRO's S-band radar for tracking ground surface shifts. Observing through clouds and forests is a standard radar capability. The specific engineering challenge here was overcoming a physical paradox that historically forced researchers to choose between capturing fine-grained detail and maintaining total global coverage. This graphic illustrates the minimum antenna area constraint, a problem engineers call the Swath-Resolution trade-off. To capture extremely sharp, high-resolution pixels, a radar must fire rapidly to capture a wide Doppler bandwidth. But there is a physical penalty. If you pulse the radar too fast, the returning ground echoes start overlapping and crashing into one another before the receiver can cleanly process them. To prevent this signal overlap, engineers have to shrink the observation area by physically narrowing the radar beam to scan a tiny strip of land. Conversely, if you want to capture a massive swath of land in a single pass, you must use a wide radar beam. This forces you to pulse the radar much slower, drastically lowering spatial resolution. Historically, radar satellites faced a strict ultimatum. You could capture sharp images of a very narrow strip of land, or you could capture blurry images of a massive strip of land. To map the entire planet at a high cadence, engineers had to design a system that could physically decouple these conflicting electromagnetic constraints. This diagram shows the solution, a technique called SweepSAR. It changes the observation geometry by separating how the radar transmits and receives energy. During the transmit phase, all individual transmit and receive modules fire at the exact same time. That combined energy hits the 12-meter reflector, which acts like a giant flashlight. It casts a wide beam that bathes a continuous 240-kilometer swath of Earth in radar energy. The innovation happens on the receive end, utilizing the physical time delay of the returning radar echoes. Because the swath is so wide, echoes from the closest edge of the terrain arrive at the satellite first, while echoes from the furthest edges arrive slightly later. Instead of trying to catch this massive echo with one wide, blurry beam, NISAR uses digital beamforming to generate a narrow, highly targeted receive beam. The system dynamically activates specific receiver elements one by one. It physically tracks the echo as it sweeps across the feed array at the speed of light. The unified transmit phase guarantees the massive swath width, while the digital scan-on-receive tracking isolates the signal, preserving the high resolution without compromise. Even with SweepSAR handling the swath geometry, there is another variable. The satellite is flying forward along its orbit at immense speed. Because the swath is 240 kilometers wide, the hardware must use a lower physical pulse rate. It must wait long enough for that massive echo to return before firing the next pulse. A low pulse rate typically causes azimuth aliasing, a persistent blurry smear across the final image in the direction of flight. This signal math schematic details the solution, the Displaced Phase Center Antenna Technique, or DPCA. The radar utilizes multiple independent receive apertures spaced out perfectly along the flight path. For every single pulse transmitted, these displaced receivers capture the returning echoes simultaneously from slightly different spatial vantage points. By combining this multi-channel data during processing, the system artificially boosts the sampling rate. The mathematically calculated effective pulse rate becomes much higher than the physical pulse rate. DPCA lets NISAR operate at a low physical pulse rate to capture the wide swath, while digitally achieving the high-frequency Doppler sampling required for sharp resolution. One final hardware limitation remains. A monostatic radar system cannot transmit and receive at the exact same time. Doing so would overload and destroy its highly sensitive receiver electronics. Because a 240-kilometer echo takes longer to return than the interval between pulses, the radar must fire its next pulse while the previous echo is still arriving. During those brief transmit moments, the receiver shuts off. If the pulse intervals are kept mathematically uniform, this creates persistent blend ranges, solid black stripes running directly down the length of the radar image. To solve this, the signal processing relies on staggered SAR, also known as PRF dithering. By continuously and cyclically varying the interval time between pulses, the system breaks up those solid black stripes, dispersing the blind spots as scattered, randomized pixel gaps across the swath. The onboard Level 1 signal processing then applies mathematical interpolation. It uses the overlapping data from adjacent pulses to mathematically fill in those randomized gaps. Staggered PRF transforms a fatal hardware blackout limitation into a seamless, uninterrupted wide swath image stream. This graphic details the final planetary scale capability generated by this integrated architecture. NISAR yields sharp radar imagery maintained across a massive 242-kilometer swath. Because the swath is so wide, the satellite achieves complete global coverage in exactly 12 days, requiring 173 orbits per cycle. This dual-frequency chart illustrates the specific targets of the data stream. The 24-centimeter L-band and 9.3-centimeter S-band are time-synced to operate simultaneously on a shared aperture without interference. This relentless coverage allows researchers to convert static maps into a dynamic, continuous time-lapse of the Earth's surface evolution. The scientific stakes of this data are massive. In the cryosphere, the system tracks changing velocities and fracture mechanics across immense glacial ice fields. Above the equator, in dense tropical rainforests, the long wavelength of the L-band radar penetrates the tree canopy to map the ground directly below. This capability gives scientists the exact data required to measure deep forest biomass and track critical agricultural shifts globally. The interferometric precision of the radar can even detect millimeter-scale tectonic ground deformations, offering crucial warning signs before volcanic eruptions or earthquakes. But the most important specification of this mission is the data policy. Every byte of L-band and S-band science data generated will be completely free and open to the public. By resolving the signal processing bottlenecks that once forced a trade-off between detail and scale, NISAR provides a high-resolution, open-access record of the Earth's surface in a constant 12-day cycle.